Hello guys, Mr. G here with another video for the grade 11 related to vectors. Last time we were talking about representing vector in a Cartesian plane. We can calculate the resultant Rx and Ry graphically, but we can also calculate it algebraically. Remember, this is from the last video or last lesson. So we have all these vectors and we can calculate the X as you have it here, and you can calculate the Ry as you have it there. Remember, this is graphically. When you calculate it graphically, you come to this point, right? But you can also calculate it algebraically. It depends the question, in which algebraically is like we did it before in grade here it is in grade 10. Okay, it's how to calculate the Rx and Ry graphically or algebraically. Okay, now here this is the new one this year. We can calculate the R of Ry and Rx graphically as it is here using two methods. We explain both methods, the tail to tail and the tail to head method. However, this one can also be calculated algebraically. So if we want to calculate the resultant force of these two Rxy and Rxx, we can just use the theorem of Pythagoras. Fr square is equal to Fr in x square plus Fr in y square. So this is how we can calculate algebraically the magnitude of that Fr vector. Okay, this is Pythagoras. Remember, this is a right angle triangle, but vectors have direction, so we have to get the direction as well. And the direction is going to be given by an angle. It could be, for example, this angle here. So this angle here, we're going to call it a theta, for instance, and we may calculate that angle. So the angle, or how to calculate that angle, could be equal by using the tan. So tan theta is equal to opposite side, which in this case is Fr in y divided by the adjacent side, which in this case is Fr in x. So this is one way of calculating the direction of that specific vector, right? But there is other. You can use sin, you can use cos. So I'm not going to write all of them because I know you can do that. And this is how to calculate the direction and the magnitude of the vector algebraically. Okay, now note the following. The direction not necessarily have to be that angle. So you can say either from the positive x-axis, which is going to be a vector that is moving clockwise, or the direction will be given by a clockwise direction in this way. So this here will give you the direction using the axis. So from here will be from the positive x-axis. Okay, and that one then is a little bit tricky. To get this direction will be 180 degrees minus the theta you did calculate. All right, and this is from or to the positive x-axis. This is the correct way of giving that specific direction. Okay, so this is, I hope it's clear, it's not that difficult. Remember, for the direction you can use another identity using sen, which is opposite divided by hypotenuse, or you can use cosine, which is adjacent divided by hypotenuse. Now let's go to the next part of this lesson. Okay, now so far we saw vectors that can be added in the x-axis and the y-axis, but all those vectors are right on the axis. If you start from here, all of them were on the x-axis, all of them were on the y-axis, and we get a resultant vector adding those resultant x and resultant y. We can use it also algebraically, but sometimes we starting with vectors like this case here that is in none of the axes. Now, when that happens, we have to determine the component of the vector. And how we do that? We have to project the vector to the x-axis perpendicular, and we have to project that vector perpendicular to the y-axis. And then we're going to have two new vectors. This vector in the x-axis is going to be called, it is a component of the first vector. This one here is going to be called f1 in x, because it's the projection of the first vector in the x-axis. And in the y-axis, this one here will give you another vector that is going to be called f1 in y. That is what we get. And obviously we can calculate those two vectors if we know the angle. If it's graphically, you just measure the angle, but if it's algebraically, then you have to use the projection of those vectors. For f1 in x, you say that is equal to f1 multiplied by the cosine of theta. This is pure mathematics, alright? And if it's the projection of the y-axis or the y component, you get that f1 in y is equal to f1 multiplied by sin theta. This is how to calculate the component of those two vectors algebraically. Now, if you notice, the combination of f1 in x and f1 in y will give you f1. So this is a way of breaking vectors into components, because sometimes you have more than one. If you have more than one and you ask to calculate the resultant, then first you have to break them into components, and then after that you have to calculate the resultant in x and the resultant in y. Let's do one simple example, because we are almost done with this first video here. Okay, so let's see this example. This example says two forces act on a point F1 of 5 Newton at an angle of 21,8 degrees to the positive x-axis, and F2 equal to 6 Newton at an angle of 160 to the positive x-axis. Calculate the resultant. Now, if you want to do this one graphically, the first thing you have to do is to draw the two vectors, and they must be accurately. So make sure this angle here for F1, you have to make sure using a protector this angle is indeed 21,8. This is not the case. I am not using protector or ruler here, just explaining how to do it. And make sure the second vector is 6 Newton, in which you can use a scale of 1 Newton is to 1 centimeter. And then you have to make sure this angle from the positive x-axis to where the vector is here, this angle is 160 degrees, that angle there. Okay, so this is the first step when you draw it graphically. You draw the vectors on the Cartesian plane accurately. Now, what are you going to do then? You are going to determine the component of each of the vectors in x and in y axis graphically. So you will have f1 in x graphically. This is not at scale, guys, so please note that one, and you will have the f1 in y also graphically. F1 in y graphically. We're working now graphically, okay? And then you do the same for the f2. You get the f2 in x. Remember, this is not accurate. You're supposed to do it with a ruler and a protector. This one is f2 in x, and then if you take it to the y-axis, you will have here f2 in y-axis. Okay, now you have f2 in x and you have f1 in x here. All right, and you have f1 in y, here it is, and you have f2 in y. There we go. So what are you going to do now to calculate the resultant? We're going back all the way to where we begin, which is this side here. You are going to calculate the resultant in x, and you are going to calculate the resultant in y using the method tail to head. Right? You will get then Rx, Ry, which is here. We've done it before in last video. And then after that you calculate the resultant of that 2rx and ry. Okay, so it's very easy. So that is how to use it, or how to do it graphically. Now, how to do it algebraically is a little bit, or maybe a little bit more tricky. Now, algebraically we have to follow certain steps. Okay, so what are those steps? This is only the first two steps. First, we make a rough sketch. In this case, we already make the sketch, so we are not going to redo it. Just the sketch of the forces, not the components. Remember, we're going to do it algebraically right now. Okay, so second step, find the horizontal and vertical component for each vector. So what is that? For F1, for the first force, we are going to calculate F1 in X, and we are going to calculate F1 in Y. Alright, using the identities explained before here by the components. There is how to calculate the components. Okay, so we're going to calculate both components, the X component and the Y component. Now here we have the horizontal component and the vertical component of F1. So you're always going to do that for F1, and you are also going to do it for F2. So let's do it for F2. And here is the answers for the components of the second force. Note that we got a negative here. This negative is because it's in the negative quadrant, mathematically speaking. You can see here it's in the second quadrant, okay? So that is important. That is why it's important the sketch to do it, and you see where is the vector allocated. Now, what is the third step you have to do? Now you are going to determine the resultant force in x-axis and the resultant force in y-axis. Remember, if it was graphically, then you will come to this point here we did in last video. If you have to do it algebraically, then we are going to do it just now. Now we are working on the axis. Okay, so in F1 we have 4,64, in F2 we have minus 5,64. So what we have? Now we are at this point where we have the resultant x and the resultant y. Now we have to calculate the resultant. We are not done yet. We just calculating the resultant x and y. Now we are going to go to this point here. So now we are at this point of the work. We're calculating the resultant. This point here using Pythagoras. This one here and that one there for the direction. Okay. So you know that everything was done in the previous video, and some of them I spoke just now when we started. So let's go to step 4. And now we are at the last step, which is calculate the magnitude and of the resultant vector and the direction. So how we calculate the magnitude? As we say, we're going to use the theorem of Pythagoras. So FR square is equal to FR in x square plus FR in y square. And if we substitute here, this is the magnitude of the resultant force when these two forces act on an object as they are here. This is the magnitude of that resultant force. But this work is not done, because remember it's a vector, and vectors need a direction. So for direction we are going to use 10. It is the easiest one. We say 10 theta. 10 theta, I will speak about theta just now, is FR in y divided by FR in x. Okay, now FR in y, it was going to be 3,91 divided by FR, sorry, this is FRY divided by FR in x, a mistake there we go, which is minus 1. So we get, this give you minus 3,91. And now how do you get theta? Theta is equal to 10 to the minus 1 of negative 3,91. And the answer is going to be minus 75,65 degrees. Now, this angle, if you notice, this drawing, where is going to be this angle? So roughly, this vector is going to be somewhere there. Alright, little bit perhaps more to the y-axis. This is the vector we just calculated, that is the vector. And this 75 is the angle from this x-axis. Alright, this is the 75,65 degree. That is that vector, but the direction must be given according to the axis. So for the final direction, you come from the x-axis all the way to the vector, and you get this angle here, which I'm not going to do it. I'm sure you can. So guys, this is all for now. We did a lot, actually, more than the previous videos. We start talking about this part here, when we can calculate it algebraically and the direction. We went back there all the way, and we re-explained that one a little bit. We saw a new case. We learned that we can break vectors into components, and we have a component method to calculate the resultant of vectors that are not on the axis. This is the way. Now this could be tricky, could be difficult, it could be long. Next time we're going to practice, we're going to mention one new concept which we didn't mention here. It's a very important concept, and it's equilibrium. We're going to talk about that one, and then we're going to do some questions to practice. Then next time we'll be doing the experiment. Maybe I will cheat a little bit and I'll make a video before the due date, because time is running, okay? And we have to start with Newton's law. But thank you for watching. I'll see you next time. Mr. G here.